what Fermi level is. Fermi level is the intermediate level in the forbidden band gap where the probability of finding electron below that level is 50% and above that level is 0. So you can say that all the electrons are present below the Fermi level, and above that only 0 electrons are present. Thus, the energy state diagram of the Fermi level you can see in this figure, and the probability of finding the electron is half over here, and maximum it's 1 and minimum it's 0. In n-type material, the large number of electrons in the conduction band moves the Fermi level up. In n-type, the Fermi level is up near to the valence band because as we know the number of electrons are more, and with the dopant being n-type, it has a donor level as well. That's why it makes the Fermi level nearer to the conduction band because the number of electrons present will be more. In p-type, the large number of holes in the valence band moves the Fermi level near to the valence band. The concentration of electron in conduction band is N0 is Nc e to the power minus Ec minus Ef slash kT, where the effective densities of the state Nc is given by this formula. The concentration of hole in the valence band P0 is Nv into e to the power Ef minus Ev, as valence band is below Fermi level slash kT, where the effective density of state Nv is given by this formula. N0 into P0 would be equal to under root of e to the power minus Eg slash 2 kT is equals to Ni square. The intrinsic concentration of silicon at room temperature is 1.5 into 10 to the power 10 centimeter per cube. This value is often not given in the examination. You can remember this value. The intrinsic concentration of germanium at room temperature is 2.5 into 10 to the power 13. Intrinsic concentration for gallium arsenide at room temperature is 2 into 10 to the power 6. N0 and P0 I have already defined with respect to intrinsic level also. Intrinsic level is that level where no dopant is added and it is almost in the middle of the forbidden gap. If a semiconductor contains both negative charge, electrons and ionized acceptors, and positive charge, holes and ionized donors, then electrostatically neutrality will be maintained by P0 plus Nd positive and N0 plus Nd negative. The mobility of the average drift velocity per unit electric field is mu n is equals to velocity divided by electric field, which is centimeter square per volt second. The current density of mobility is J q n mu n into E. I would say this is for electrons. Similarly, it could be fine for holes also, and the total current density will be Q into number of hole concentrations into the mobility of hole plus number of electron concentration into mobility of electrons into E. E is the electric field, which is equals to sigma into E, which is ampere per centimeter square. And the resistance of the bar is R equals to rho L by. You can calculate rho, which is equals to 1 by sigma into, or you can say L by sigma into A. It will be similar. Now the process of electron absorption or excess charge carrier take place because of thermal absorption and photoconductivity. When an photon whose energy, which is demonstrated by this formula h mu, h is Planck's constant, mu is the frequency, is greater than, which combines to give an energy which is greater than the forbidden gap, strikes the semiconductor surface, the intensity of transmitted electron through the sample thickness I is it is I naught e to the power minus at, where a is the absorption coefficient and the photon energy E is equals to 1.24 by lambda. This is impurity scattering and this is lattice scattering. Impurity scattering is due to the t to the power 3 by 2 and lattice scattering is t to the power minus 3 by 2. There are two types of scattering that take place when a photon strikes a semiconductor. The Hall coefficient. When a magnetic field is applied perpendicular to a charge carrying semiconductor, F is equals to Q into E plus V cross V, where velocity into magnetic field plus the electric field, when applied on a charged particle, presents a force that deviates the charged particle. A steady state flow of nodes down the electron or down the length of bar, the electric field Ey must balance the product Vx so that the net force is y direction. It should be in y direction is 0. Thus the electric field Ey is known as the Hall effect and the resulting voltage V equals to EW called a Hall voltage. The proportionality constant RH is equals to 1 over Q into P naught. Q is the charge value and P naught is the concentration of charge carriers, where rho is equals to Vi over La, which is the direct formula, but if you see, we are actually calculating the charge carriers over here by this proportionality constant, and thus the mobility is equals to the charge carriers divided by, or the Hall coefficient divided by the resistivity. These are the various important formulas that we derive from Hall coefficient. What is Hall coefficient is? Hall coefficient is the direct